We're going to continue our discussion of reaction rates and equilibrium. In Lesson 2, we're going to talk about factors that affect reaction rate and something else called potential energy diagrams. By the end of this presentation, you should be able to list 5 factors that affect the reaction rate, define exothermic and endothermic as chemical reactions, and identify the parts of a potential energy diagram. The order of presentation will be to review a little bit from last class, talk about factors that affect reaction rate, define exothermic and endothermic reactions and give examples, talk about the parts of a potential energy diagram, and then give you a chance to do some practice, and then we'll finish up with some review. In the last class, we defined what a reaction rate is. It is how quickly reactants turn into products. And there are various things that can affect how fast this happens. One of them is concentration, which in the last unit we measured as molarity. The next thing that can affect the rate of reaction is temperature. Another factor is something called surface area. Pressure is something that can affect the rate of a reaction. And then lastly, something called a catalyst, which I'll define in a few slides. Generally speaking, the reaction rate is dependent on the number of effective collisions between reactant particles. So any of these factors that will increase the number of effective collisions will increase the rate of a reaction. As an example for concentration, with a low concentration, there are not very many collisions between particles, so the rate is slow. If you increase the concentration, there are more molecules to react, and this increases the likelihood of an effective collision. So increased concentration will generally increase the rate of a chemical reaction. Temperature is another factor that affects the rate of a reaction. At low temperature, molecules move slower than at higher temperatures. So as temperature increases, the molecules speed up and increase the likelihood that there will be an effective collision. As a result, the reaction rate will tend to increase. Surface area tells us how many molecules are available to react. Generally speaking, increasing the surface area allows more molecules to react, speeding up the reaction. Pressure is a result of molecules bouncing off of each other and the walls of its container. As we learned in the gas laws unit, pressure is very much dependent on the volume the gas is in. An increased pressure caused by a decreasing volume will cause more collisions because there is less space to move around. On the other hand, a decreased pressure caused by increasing volume causes fewer collisions because there is more space to move. So generally speaking, increasing the pressure of gases will increase the rate of the reaction. We've used a catalyst in a couple of labs this year, but we're going to look at it a little bit more closely. A catalyst is a chemical that speeds up a reaction by bringing chemicals together. In effect, a catalyst lowers the activation energy of a reaction. And we'll talk about what activation energy means in a little bit. But basically, the green substance here is a catalyst, and it brings two molecules together, causing them to react more quickly. So adding a catalyst speeds up a chemical reaction. In last class, we talked about effective collisions. One of the criteria to make a collision effective is to have enough energy. You'll study this in physics next year in more detail, but for now it's enough to know that energy is the ability to do work. And the SI units of energy is the joule, and very often in chemistry you'll see it measured as kilojoules, with the prefix kilo meaning 1,000. 1,000 joules is 1 kilojoule. Now, one way we can identify energy in a chemical reaction is whether it is exothermic or endothermic. An exothermic reaction is one that releases energy to the surroundings. An endothermic reaction is one that absorbs energy. We're going to talk about these in more detail now. As we said, exothermic releases energy. One way to remember this is that the prefix exo means out or away from, just like exit. In an exothermic reaction, heat or light is produced by the reaction and is given off to the environment. As a result, it makes things feel warmer. Again, you can remember that heat exits the reaction. Some real-life examples of exothermic reactions are fireworks, a campfire, an instant hot pack, and even a Some phase changes that are exothermic are freezing and condensation. They are exothermic because they release heat. An endothermic reaction occurs when heat energy is absorbed by the chemical reaction. It is called endothermic because endo means going into or absorbing. In an endothermic reaction, the heat is absorbed, and therefore it will feel colder because it is, in effect, sucking heat away from its surroundings. Some examples of endothermic reactions are baking, cold packs, and photosynthesis when plants absorb energy from the sun to create food. Phase changes that are endothermic include melting and vaporization because they require heat energy to occur. So in summary, endothermic and exothermic are types of chemical reactions that involve heat. Endothermic absorbs heat, and exothermic releases heat. Chemists will often show the change in energy of a reaction in something called potential energy diagrams. Basically, they are graphs that show the change in energy of a reaction. In an endothermic reaction, the reactants start off lower than the products because they absorb energy from the environment and the products end up higher. In an exothermic reaction, the reverse happens. The reactants start off high, release energy to the environment, and the products end up lower. This is the general shape of a potential energy diagram, and you will be asked to know all of its parts. The first thing to notice is that the reactants don't turn straight into products. There's a hump here in the middle, which indicates there's more energy involved in getting this to happen. First, the parts. This arrow down here represents the energy of the reactants. Over here, we have the energy of the products. This arrow represents the activation energy of the reaction, and that means how much energy you have to give the reactants to get them up over this hump. A real-life example of this would be as if you had a boulder over here and needed to roll it to this side of the hill. The activation energy refers to the amount of energy needed to get it to the top of the hill. Once it's here, it will naturally fall over to the other side. At the top of the hill, we have something called the activated complex. It's kind of a middle step between reactants and products. This arrow right here represents the activation energy of the reverse reaction. And by reverse, I mean we take products and bring them backwards, or in the reverse, to reactants. The next arrow you're going to ask to be aware of is this right here. This represents the heat of the reaction, abbreviated delta H. Another way to think of the heat of the reaction is it's the difference in energy between the products and the reactants. This represents an endothermic reaction because the products end up higher than the reactants. For an endothermic reaction, the delta H is positive, indicating a gain in energy. The last thing that you're going to be asked to know on a potential energy diagram is what happens if you put in a catalyst. Generally, a catalyst will lower the activation energy. So rather than being a high hump right here, you will generally see much lower energy needed to get this going. This happens because a catalyst will bring chemicals together, requiring less energy. What do you think the potential energy diagram would look like for an exothermic reaction? Here it is, the same basic shape. We have reactants and products. We have activation energy to get us up over the hill. But notice here, the delta H goes down. The products are lower than the reactants. For an exothermic reaction, the delta H is negative, indicating a loss in energy by the reaction. Here's some practice for you to try. Take a look at each of these questions and see if you can identify the amount of energy involved in each. You might want to pause here and try to do this on some scratch paper. What is the total energy of the reactants? That's this amount right here, and that represents 40 kilojoules. What is the total energy of the products, C and D? That's this amount right here, and that represents 20 kilojoules. The heat of the reaction is the difference in heat between the reactants and products. That's this amount right here. So it's the difference between 40 and 20. But because the products ended up lower, it's actually negative 20 kilojoules. Is the reaction endothermic or exothermic? Well, because the change in energy is negative, that makes it an exothermic reaction. What is the energy of the activated complex? The activated complex is up here at the top of the hill. So it's the total amount of energy from there down to the bottom, and that would be 100 kilojoules. What is the activation energy of the reaction? That is the amount of energy you need to get from the reactants to the top of the hill. The reactants are at 40, and the top of the hill is at 100. The difference in those two is 60 kilojoules. Now consider the reverse reaction read right to left. That's in this direction. Calculate the heat of the reaction. So it's still the difference in heat between the reactants and products, but in the reverse, A and B are higher than C and D, so it's going to be positive 20 kilojoules. Is the reaction endothermic or exothermic? It's going to be endothermic because of the positive heat of reaction. And then what is the activation energy for the reverse reaction? That's the amount of energy needed to go from C to the top of the hill. And that's from 20 to 100, and that represents 80 kilojoules. So that's it for today. At this point, you should be able to list the 5 factors that affect the rate of a reaction, define exothermic and endothermic reactions and provide examples of each, identify the parts of a potential energy diagram for a chemical reaction. By the end of the day, you should be handing in an Ed puzzle review, the reaction rate worksheet, and the distance learning plan review. Here's the extra credit. In your DLD review, if you can include an emoji that represents how you feel, not just about chemistry, but just in general, I'll give you some points. If you can tell me why that's how you feel, I'll give you a couple more. And if you're feeling really crazy, instead of an emoji, give me a GIF that describes how you feel, and I'll give you the most points possible. Just as a heads up, in the next class, we're going to do an at-home kitchen lab. As always, email me if you have any questions.